Hello everyone. I am myself Arnav Amit Chete. I am a second year student of mechanical engineering in Diva Patil Akudi, and today I am here to tell you about thermodynamic processes. Okay, let's dive into this. Here is a roadmap for a sequential tour of thermodynamic processes today. First, we'll define a thermodynamic process today. Then we'll break down isothermal and adiabatic process, move on to isochoric and isobaric process, explore cyclic process, and finally take a look at reversible versus irreversible processes. Part 1, Defining a thermodynamic process. Let's set a quick baseline. What exactly is it at its core? Well, at its simplest, a process is just a system transforming from one equilibrium state to another. What's the cylinder animation? In step 1, you've got 4 weights sitting on a piston. That's our initial state. In step 2, we just take 2 weights off. Naturally, by step 3, the piston rises. Boom, the entire state just changed, and energy was transferred along the way in the form of heat. Then, moving on to part 2, isothermal and adiabatic process. Let's see how Greek roots can actually help us decode this science here. First up on our 2 is isothermal process. The name really gives it away. It's derived from Greek word isos meaning equal and thermon meaning heat. Equal heat. Basically in an isothermal process, the temperature of system stays absolutely constant as it changes from start to finish. The initial and final temperature are totally identical, meaning change in temperature represented by dt is zero. In this brilliantly illustrate the concept. Just watch this boiling water over fire. Even though water is actively bubbling away and literally changing its physical state from liquid to gas, entire process actually occurs at totally constant temperature. Crazy, right? Our second stop is adiabatic process. The word comes from Greek word abdia, which translates to impossible. Now, exactly what is impossible here? Well, in this perfectly insulated system, it's impossible for heat to be lost or gained. There is zero exchange of heat between system and outside, meaning dq is equal to zero. The energy transfers purely as work, kind of like a totally frictionless piston rapidly pumping up and down without a single drop of heat escaping. For a perfect real world anchor, just imagine storing hot water in an ideal thermos flask. Because the thermos doesn't allow heat transfer through its thick insulated walls, the system inside is perfectly isolated. Let's move on to part 3 and see how this builds. Isochoric and isobaric process. Now we are dealing with volume and pressure. First, let's take a look at isochoric process. This combined isos for equal and core for space or volume. This means the volume remains completely constant during the change. You might also hear it called as isovolumetric or isometric process because the physical space neither increases nor decreases the change in volume. dV is precisely zero. Going back to a boiling water example for a second, an isochoric process would be boiling that water inside a tightly closed vessel. Because vessel is totally sealed shut, the volume is trapped. It simply cannot expand or shrink. Next up is isobaric process, again deriving from isos for equal and baros for weight or pressure. So here the pressure of the system stays perfectly constant. The initial pressure equals the final pressure, meaning change in pressure dp is equal 0. To contrast with the closed vessel we just looked at, an isobaric process is like boiling water in an open pot. Because it's completely exposed to air, the water boils entirely under a constant unchanging atmospheric pressure. Alright, part 4, the cyclic process. Let's shift our focus to system working in a loop. A cyclic process is pretty much exactly what it sounds like. It happens when a system completes a whole series of thermodynamic changes and ends up right back to at its original and initial state. Because the start and finish lines are exactly same, the net change in thermal energy is a big fat zero. Therefore, du is equal to 0 and dh is equal to 0. The ultimate classic real world anchor for a completed cycle is the famous Carnot cycle. As you can see in this looping engine animation, fuel burns to convert heat energy into mechanical work, completing the cycle and totally resetting the system back to its initial state so it can fire all over again. So the crucial point is right here on this matrix. Seriously, I would take a screenshot if I were you. It perfectly summarizes the mathematical constants of our entire thermodynamic tour: temperature, heat, volume, pressure, and internal energy. If you understand these 5 equations, you understand the processes.